Problem number 1, right? So you're told that there's a particle of mass m that's projected from point A with an initial velocity v naught, right, perpendicular to the line OA, and it moves under a central force that is directed away from the center of force O, right? You know the equation of the path, right? It's defined by this expression. And when the question says using equation 12.225, they're just talking about using the conservation of angular momentum. The question is asking you to express the radial and transverse components of the velocity v of the particle as this angle theta changes, right? So basically what we have to do is find out VR and V theta, right? So at this position, if we look at it, so you're asked to find VR and V theta like that, right? So getting right into it, knowing that it's acting under a central force, right? So since particle is under a central force, what can we say about the angular momentum per unit mass, or our quantity small h? What can we say about this? Is it going to change? How does it change? What happens to it?
Is it constant?
It stays constant, right? You have a central force. So we just learned today that it's going to be constant, right? So next, if you go in and use this expression of conservation of angular momentum, in general, you can say that this is equal to r squared times theta dot, right? And that is going to equal your initial angular momentum, right? And the good thing about the initial angular momentum is we know what v theta is, right? Because you can write this as being equal to r naught times theta dot, r naught times theta naught dot, right? Like that. What is r naught times theta dot O equal to?
Is it 0?
Nope. Right? Remember, looking at polar coordinates, right? So this is your position vector, right? So if you look at your unit vector, that'll be ER and that'll be E theta, right? Initially, what is the velocity in the R direction, in this ER direction?
Is it 0?
0, right? And what is the V theta in the theta direction? What's the velocity in the theta direction?
Equal to V naught.
It's just V naught, right? It's the scalar quantity associated with V naught. But we also know that in the theta direction, how can we write the velocity? R naught times theta naught dot, right? Is that clear, everyone? Right? Remember, when you're looking at transverse and radial components, you can always write that VR is equal to r dot, right? And V theta is equal to r times theta dot, right? Polar coordinates. So that's that. So what that means is that I know what my angular momentum is going to be per unit mass. It's going to be constant, and it's just going to be r naught times your scalar quantity v naught. Is that clear, guys? Do you want me to go over that one more time?
Yeah, can you actually?
Yeah, of course. Right. So you know that your angular momentum, as we defined it today, per unit mass is just equal to, at any position, is just equal to r squared times theta naught, right? So it's your position squared times the angular velocity theta naught, right? But we know that it stays constant, right? So we know it's going to equal the initial angular momentum per unit mass, right? So that's h naught over here. That can also be written as, I guess I skipped a step here, right? That is equal to r naught squared times theta naught dot, right? So it's your initial position squared times your initial angular speed, right? Opening this up, I can write this expression as r naught times theta dot naught, right? And this is nothing but your initial v theta, right? And we know from the problem statement that in the theta direction initially, the velocity is v naught. So it just becomes v naught over here. Make sense?
Yeah.
All right, thanks. What that allows us to do is that allows us to write our theta dot term, right? We can write that theta dot is basically just equal to r naught times v naught divided by r squared, like that. All right. And we know from our expression, from the question, that r is equal to r naught divided by the square root of cosine 2 theta, right? So this expression here, just plugging in for r, that becomes equal to r naught times v naught. The square root of cosine 2 theta comes on the top, gets squared, becomes cosine 2 theta. And down below, you have r naught squared, like that, right? So that r naught cancels out. So you're left with v naught times cosine 2 theta divided by r naught, like that, right? That's it. We basically done everything we need to solve the whole problem, right? Because, and this was just, maybe we did it a little bit backwards, but for the radial component of the velocity, right? We know that that's equal to VR, right? We know that that is just equal to r dot, right? And we know that r dot is dr over dt, and that can be written as dr over d theta times d theta over dt, right? So this is just equal to dr over d theta times theta naught, right? So it's basically if the theta naught, if you plug in for what we found, so that's just equal to v naught times, well, you know what? Let's just keep theta naught as it is for now. So you have theta naught and then dr over d theta, we can find out, right? Because r is in terms of theta in the expression, right? R naught is a constant and theta is changing over here. So this just becomes theta naught times d of r naught square root of cosine 2 theta, right? So you take the derivative of this expression inside with respect to theta, and I'm just going to write the answer out, but you guys know how to do the differentiation, right? Your cosine 2 theta to the power of minus half, the minus half comes down, right? This becomes to the power of 3 over 2 and plus 1. Then you also have the 2 theta term, so there's a 2 that comes out of it, right? There's also a cosine 2 theta in here, so there you get a sine 2 theta term on top, right? How do you guys feel with differentiation? if you're not sure, Mathematica can just do it straight away for you. It'll give you the answer. But anyways, the derivative of this guy is just R naught times, R naught comes out, you have theta naught times, what you end up with is sine 2 theta divided by cosine 2 theta to the power of 3/2. Do you guys want to go through how to differentiate this? Basically, d by d theta of cosine. All right, let's just do it. To the power of minus half, right? So that the minus half comes down. Cosine 2 theta is minus sine 2 theta, and then 2 theta has the 2 outside. So that. And this becomes to the power of plus 1, right? So 3 over minus 1, right? So 3/2. So cosine 2 theta, 3/2. Good. Okay. So this is what we get. And then we plug in for what we found for theta naught, right? So plug in for theta naught, right? So you end up with this expression being equal to R naught times, what did we find? V naught over cosine 2 theta divided by R naught times sine 2 theta divided by cosine 2 theta to the power of 3/2. Like that, right? So R naught cancels out. Cosine 2 theta, that becomes 1. Half like that. So you end up with VR is equal to V naught times sine 2 theta divided by the square root of cosine 2 theta. Like that. All right, questions, guys? Does this make sense at all? You good, right?
Is that that v cosine 2 theta over r? Is that just the theta dot from above?
That's right.
Thank you.
Yep. Someone else was saying something. No? All right. Next, you can write the transverse component is really easy because with the transverse component of velocity, it's directly related to your angular momentum, right? That's what we saw in class today. So the transverse component of velocity is just v theta. That's always going to equal your angular momentum divided by r. Right? Do you guys understand why this makes sense? Because we'd said that h is equal to r squared times theta dot, which is equal to r times theta dot, and this term is equal to v theta, right? Good. So this you just plug in for what we'd found above, right? What you end up with is R naught V naught over R naught times cosine 2 theta. R naught cancels out. So you're left with V theta is equal to V naught times square root of cosine 2 theta. Good. All right. Let's look at the next question. So with the next question, it's basically the same question, but what you're asked to do is that you're asked to show that the velocity of the particle and the central force F are proportional to the distance r from, so this distance r, to the central force O, and you're asked to show that the radius of curvature of the path is proportional to r cubed, right? So from the previous question, we had found that we had said that H was just equal to R naught times V naught, right? And we'd also said that theta dot is equal to V naught over R naught times cosine 2 theta, right? And we'd also found that what we derived, yep, we'd also found R dot, right? So we'd also found the term for R dot. So R dot was equal to V naught times sine 2 theta divided by square root of cosine 2 theta. Right? Okay. So now, in order to relate it to our central force, right? The only expression we need to worry about is, wait, where are my notes? Did I shut those down? Anyways, all right. Oh no, I'm looking at the wrong ones. The only expression I need to worry about when I'm trying to look at the force is this expression number 8 over here, right? Because that's the only one that's relating my central force to the terms inside, right? So what I need to do is I need to find theta dot. I know R, I know theta dot, so I just need to find what R double dot is. And we get set up for success. Hey, Seamus, easy. Take it easy. Just give me 1 second, guys. Just went outside. Just went outside. Relax. Relax. Yeah. Sorry about that, guys. All right. So, in the spirit of doing that, we need to find out only, right? So let's just write that expression out. So if we look at our notes, so for the force, right, we saw that minus F is equal to M times R double dot minus R theta dot squared, right? So all we need to worry about, everything else is known, we just need to find out what R double dot is, right? And the velocities we'd already solved in the previous question, so we can do those easily. Okay, so to find R double dot, that's R double dot like that. So, you know, skipping a few steps, you guys should be experts at this by this point. This can be written as dr dot over d theta times theta dot, right? So basically you have theta dot times the differential with respect to theta of your R dot inside here. So that's just V naught sine 2 theta divided by cosine square root of cosine 2 theta, right? And now the differentiation gets a little bit more complicated. Again, if you're not comfortable doing that, Mathematica can do that very easily for you, right? We've run out of time, so I don't have time to demonstrate that for you guys, but use Mathematica to do your differentiation. I know MATLAB can do it as well, right? So The V naught comes out, it's a constant, V naught, theta dot, and you end up with the differential of this big mess inside is 2 cosine squared 2 theta plus sine squared 2 theta divided by cosine 2 theta to the power of 3/2, like that. And we plug in what we know for theta dot from up here, and you end up with the expression for r double dot. Right, so r double dot, after doing all of the simplifications, you end up with the expression that's equal to V naught squared over R naught times 2 cosine squared 2 theta plus sine squared 2 theta, right? That is divided by the square root of cosine 2 theta. All right, so we had found out what VR and V theta were in the previous equation, right? But we need to get R back into the picture. Previous ones, we found out everything without the R, right? So if we look at that, quick, so this is for part A, you see that VR is just equal to R dot, right? That ends up being V naught sine 2 theta divided by cosine 2 theta. But then, you use this expression over here, right? We know that from the question that that equation is true, right? So R is equal to R naught divided by cosine 2 theta, right? Or you can say that cosine 2 theta is equal to R naught divided by R, right? So you can write this expression as V naught R over R naught times sine 2 theta. Right, and you can write V theta, which we know is R theta dot, as just being equal to V naught R over R naught, right, times cosine 2 theta, right? So we're just plugging in what we know the value of theta dot is. Right, so that's this guy here, and that guy over there. All right, so then you can straight away say that our velocity is going to be, you have your two orthogonal components of VR and V theta, so just VR squared plus V theta squared, like that, right? The magnitude of the velocity. Plugging in from these two expressions here, what you end up with is the constant V naught R over R naught gets pulled all the way out outside your square root. You end up with inside what you end up with is sine squared 2 theta plus cosine squared 2 theta. And what is this equal to? Sine squared 2 theta plus cosine squared 2 theta.
Is that 1?
That's just 1, right? Right? So question was asking you to show that the velocity of the particle is proportional to the distance r. V naught and R naught are constants. So say that V is proportional to R. All right. And then for our force, all right, guys, we're going to go a little bit over time. It seems to be a theme of our class. I'm sorry. For the force, we have to use this expression over here. All right. So to use that expression, we need to write what the acceleration in the radial direction is, right? So that AR is equal to R double dot minus R theta dot squared, right? We'd written what R double dot was right over here. We know what theta dot is. right? So it's just plugging. And again, if you're gluttons for punishment, you can do this by hand, but doing it in Mathematica make life much easier. So we plug everything in, get V naught squared over R naught times 2 cosine squared times 2 cosine squared 2 theta plus sine squared 2 theta divided by square root of cosine 2 theta minus R naught divided by cosine 2 theta times V naught squared over R naught squared times cosine squared 2 theta. Right? You add these up, what you see is that goes, you're left with V naught squared over R naught, 2 cosine squared 2 theta minus cosine squared 2 theta, you end up with cosine squared 2 theta plus sine squared 2 theta divided by the square root of cosine 2 theta. And again, that's equal to 1, right? So you end up with V naught squared over R naught times the square root of cosine 2 theta. And again, you plug in cosine 2 theta equals R naught over R. You end up with the expression that this is equal to V naught squared R over R naught squared, like that, right? So again, you've shown that the force is equal to V naught squared over R naught squared times R. So F is also proportional to R, like that. Well, it's going to equal the mass times that, obviously, right? Because you have MAR. And, okay, all right, skip a step. Sorry. F minus F was equal to MAR. But you're told that F is pointing away from the body. So it's actually plus F, right? So your F is equal to M V naught squared over R naught squared times R. Or basically, your F is proportional to R, like that. All right, don't worry about part B. We'll just skip over that one. All right, thanks, guys.
I have a question about Mathematica.
Yep.
What is your experience with